So one-dimensional transient conduction problems come in 3 different versions. Lumped capacitance is probably the scariest sounding, but it's actually the easiest type of problem. Medium difficulty is going to be your sudden convection, one-term approximation type problems. And then the hard problems are where you can't even use the one-term approximation, but good news is you probably won't actually see those in your heat transfer course. So the good news here is that this problem is lumped capacitance, and we're going to be able to knock it out pretty easy. So I start off every problem with given, find, concept, assumption, solution. And as I'm parsing this problem statement, it's probably worth a few comments about what annealing is. So every mechanical engineer should understand basic terminology about manufacturing and metalworking processes, things like strain hardening. And annealing is one of those terms. So the purpose of annealing is to make metal more pliable, make them easier to work with. And so annealing is done by heating up a metal to a very high temperature above its recrystallization temperature. So when you heat up metal, the atoms themselves actually realign. And what this will do is this will make your material more ductile, less brittle. And then a downside to this, though, is it becomes less hard. So you sacrifice hardness to increase ductileness. And this makes your metal easier to shape. That's its main purpose. Annealing is you heat it up to make it easier to shape. So since I know the temperatures for each of these metal balls is starting at 900 degrees and cooling to 100 degrees, that's a transient conduction problem. But what I don't know yet is what method I'm going to be able to use to solve this problem. I don't know if I can use lumped capacitance or sudden convection. So I leave my assumptions blank for now, and each time later I make an assumption, I'll go ahead and write that in. But the first part of my solution is going to be to figure out whether or not I can do the lumped capacitance method, because that's the method I want to use. That's the easy one. So every one-dimensional transient conduction problem will always start off with calculating the Biot number. And you want to see a Biot number less than 0.1. If it's less than 0.1, that means you get to use transient conduction and you've got one of the easy problems. Easier problems might be better to say. No heat transfer problem is going to be easy. It's just like hard and less hard. So the Biot number is going to be very frustrating to students because you'll see multiple different equations for it in different contexts. Sometimes you're going to see HL over K. Sometimes you'll see HV over KA. Where essentially this length, characteristic length L, is sometimes replaced by V over A, volume divided by surface area. Sometimes characteristic length and V over A will be the same thing and it won't actually matter, but for spheres they actually will be different sometimes. When figuring out whether or not you can use lumped capacitance, always use V over A. Because the lumped capacitance method, what it actually means is that you're assuming that the entire object is one temperature. You're assuming that the center of the object and the surface of the object are at the same temperature. Lumped capacitance, right? This is a lumped heat capacity. You're lumping the entire thing into one single temperature. And so what you want to know as your characteristic length when determining whether or not you can assume this is all one temperature is you want to know this ratio between the volume of the object and the surface area of the object. So it doesn't matter whether you have a nice clean object like a wall or a cylinder or a sphere or a weird oddly shaped object. You want to know the ratio, surface area to volume, since that's going to be useful in determining whether the center and the surface will be at the same temperature. And that's going to be even more important than the actual size, like the actual radius. So plugging in numbers, I was given a heat transfer coefficient of 75, but I was not given the value K for the 0.5% carbon steel. So I've got to go to a table in the back of my textbook to find that. And so now we're going to have to make our first assumption. Because carbon steel has a different value of K at different temperatures. The hotter it gets, the smaller the value for K ends up being. And we've got a huge range of temperature here, from 100 degrees all the way up to 900 degrees. So we see a range of K values at 100 degrees of 52 versus 900 degrees will be around 30. I'll pick a number kind of in the middle of 42 watts per meter Kelvin, and I'm also going to assume that this value is constant. Heat transfer problems get way more complex if you account for material properties like K changing as you change in temperature. So for your heat transfer course, I can pretty much guarantee that you are always going to assume constant material properties. So for a case like this, just pick a number kind of in the middle, make an assumption, and just go with it. Don't sweat it too much. You don't have to interpolate and make it totally perfect. Just pick something kind of close to the middle and go with it. So we're plugging in volume of a sphere, 4/3 pi r cubed, and surface area of a sphere, 4 pi r squared, and we get 0.00238. And at this point, you should be fist pumping because we're less than 0.1, which means that we can assume lumped capacitance. We can use the lumped heat capacity method, which means that we're assuming that the center of the sphere and the outer surface of the sphere are the same temperature. And that's your easiest possible case, so this is really good news. So this lumped heat capacity assumption is usually going to work for metals with high K values, because look, K is in the denominator. So the larger your value for K, the larger your denominator, which means it's easier for heat to transfer within the metal itself. So if the surface changes, heat travels very easily to the center. So that keeps the center and the surface near the same temperature. The other thing you're looking for lumped heat capacity is a low value for H. Since H is in the numerator, if you had a fan blasting on the surface, if you had a really high convection coefficient, if you have forced convection, you'll get a really large value in the numerator. And that's going to make it really easy for the surface to really quickly change temperature before the center has a chance to catch up. So lumped heat capacity is mainly going to be used in cases where you have things like metal with a really large value for K, and in places where you only have natural conduction, where you have a really low value for H up in the numerator. Right? And this Biot number essentially is a bit of a ratio between conduction inside your metal and convection out to the air. And again, this V over A is the characteristic length when determining whether or not you can use lumped capacity. In some other contexts, though, this characteristic length will not always be V over A. In some other types of problems, like sudden convection problems, you might just use like the radius or half of the wall length as your value for LC. So whenever calculating the Biot number, just double check to yourself that you're using the right characteristic length for this particular application of the Biot number. It'll change in different contexts. So now go ahead and grab your lumped heat capacity equation from your textbooks, or I'll grab this from the FE reference manual. And it should look like an exponential function. In particular, an exponential function with a negative exponent. So we've basically got a ratio of temperatures here. On the left side, we've got the final temperature compared to the ambient air, T infinity. And on the right side, we've got the initial temperature compared to the ambient air and this negative exponential term. So to understand this equation, a negative exponential is going to start off at 1, and as time increases is going to go to 0. So consider that at time equals 0, this exponential term will be 1. That's going to mean that our ratio of temperatures on the right side and left side will be equal to each other. We're just multiplying by 1. And that's going to mean that our temperature is equal to the initial temperature, which makes total sense at time 0. But then as time gets very large, this e to the negative t, so e to the negative infinity is going to be 0. So the right-hand side eventually is going to go to 0 as time approaches infinity. Which means that the left-hand side, our final temperature, will approach T infinity. It'll approach ambient temperature, which also makes sense. The longer in time we go, the object should cool to ambient temperature. And this value beta is a time constant. It's going to affect basically how quickly temperature will change. And this value beta is HA over rho VC, right? So the numerator is the convection coefficient that we were given times the surface area being 4 pi r squared, and the denominator, density times volume, which is basically mass. So this denominator is MCP, mass times heat capacity. And CP was also not given in the problem statement, so I got to go back to my table and look that up. I get 465, and that's in joules per kilogram Kelvin. And you may want to always be mindful as to whether CP is in joules or kilojoules. You'll sometimes see those written in different units. All right, so some calculator work. 0.015 is my value beta, which is my time coefficient. And I can divide temperatures over So your TA shows up right here just as we're about to get the final answer. So I do a natural log of both sides to get rid of the exponential term. And you get a value of t 167 seconds, about 2.8 minutes. So that means that each individual sphere takes about 168 seconds for itself to cool from 900 degrees to 100 degrees. And I'm sorry your TA Indy is always up here staring at me with his back to the camera. He doesn't actually understand what the camera is. I can try to get him to turn around and look at you, but he would think he's just staring at a wall. He wants to look at me, sorry. All right, so if your TA Indy looks up at the camera here, maybe you can give him a thumbs up if you think he helped out a little bit on this problem. All right, so second part of the problem is to find the total heat transferred to the atmosphere, right? If this is a factory and we've got all of this metal cooling down hundreds of degrees, all of this heat is going into the air into the room. This is essentially gonna affect like the air conditioning bill, right? You have to run fans, all of this heat has to go somewhere. So think back to thermal, you've got Q dot equals M dot Cp delta T, and we can remove time from that equation and just get the amount of heat in joules is equal to mCp delta T. So for each individual sphere, the amount of heat that it emits is its mass times Cp times its change in temperature. That's how much heat it's losing. And that's not in watts, that's just joules. That's just an amount of energy. So we can plug in density, volume, the change in temperature, and we get 781 joules per ball. So each sphere that cools down is going to emit 781 joules into the environment, just into the factory air, into the atmosphere. But we were also given in the problem statement that every hour, this factory anneals 2,500 balls each hour. So 781 joules per ball, 2,500 balls per hour, and then 1 hour is 3,600 seconds. And that gets us to 543 watts. And so it doesn't actually matter how much time each individual ball takes to cool down. If we're just trying to figure out how much heat goes into the environment, we just need to know the number of heat per ball and the number of balls per hour. It doesn't matter if each individual sphere takes 1 minute to cool or 60 minutes to cool. It just matters how much energy they each release and how many of them we're processing in the factory. Now, one assumption we made in this problem that I forgot to write down is that we ignored radiation. I only looked at convection. But each of these really hot metal spheres would actually be radiating heat to the environment as well. And so if you want to see an example problem where we include radiation, then that's the next video linked up on the screen now.